Hello, welcome to Part B of the General Theory on Calculus Variations. This is a lecture meant for advanced undergraduates or intermediate graduate students in either mathematics or physics. In this lecture, we will talk about the basic tools needed to extremize or minimize functionals. In brief, I've got here on this one page, it outlines everything. There's some symbols and there's some words, and we're going to connect the two. We already know what a functional j of y is. We're going to talk about, well, what does it mean to be a local or global extrema of a functional? And when we're talking about minima, we need to talk about possible variations of contenders for the minima. So there's a subject on admissible variations. Then there's something called Gateau variations, which is the generalization of the derivative of a function. For functionals, you get a Gateau variation. I'll say something briefly about something called the Fouché derivative. We won't use it, but you should have seen it at least once. Then once we have these tools, I will derive necessary conditions for finding extrema. And this is extremely important. This is the thing that will let us determine Euler-Lagrange equations for equations of motion in physics, for example. That on its own, this condition, it's like saying if I know the derivative vanishes, do I know it's a minimum or a maximum or a global min or a global max? If I was dealing with regular functions, setting the derivative equals 0, it just tells you local behavior. And that's the same here. So the question comes up, what more can you say? And to determine if local min or max is a global min or max, we have to talk about the convexity of the functional, which I'll define and show you a few examples of. We won't really do too much on that, but again, it's the generalization of the second derivative test, say. Okay, so let's get on with it. We're trying to find maxima or minima, and I'll say the word extrema. It means that it could be a min or a max. And we're going to now restrict ourselves to admissible sets A that are subsets of normed linear spaces. So there are many types of normed linear spaces, but in our case, they're typically function spaces. And so we're trying to find the minimum of J on some subset of a function space A that's got a norm affiliated with it. What's the definition of global min and local min? Well, if J was a regular function, a global min would mean some y bar where it attains the smallest possible value of all y's in the entire set. In other words, if I take the value of the functional at y bar, it's always going to be less than or equal to any other value that I can attain for every possible y in A. So out of all the y's in A, it gives you the smallest value. Local min basically says it's the same thing, except that the statement is true, this statement here, y bar is a local min, if y is sufficiently close to y bar. And the question there, when we're talking about sufficiently close, when you're doing a normed linear space, you mean when the norm defining the distance between the two things is small. So what I've defined here is this is a delta neighborhood of y bar in a vector space with a norm. So this is the set of all y's that are at most a distance delta from y bar. In R2, this would just be it would be a disk In R3, it would be a sphere. But these are actually function spaces, so it's you can't really draw pictures. Now, once we know what local and global min are, the general scenario is later on is that we're going to be assuming we have a candidate for the local min. We want to find that local min. And we're going to do a little trick where we compare the value of j to the value of j nearby. And what I mean by nearby is I'm going to take y bars that are a distance or a functional distance away, delta y away from y bar. Now, this statement on its own looks innocent enough, but there's a real issue, mathematical issue, is that if I start with a y bar and I just add some delta, some other function y, this sum may no longer be in the set A. So only some of these variations that I'm highlighting will be admissible, meaning precisely that it is an admissible variation only if I get something back in the set A when I add it to the y bar. Let's put this out more clearly here. So if I have a functional j defined on an admissible set A, and it's a subset of this vector space that's got a norm on it, say, contains real values, and I'm going to fix a y. The set of admissible variations of y are all of those delta y's in the vector space that I can add to it and still keep it in the set. That's what an admissible variation delta y is. Often the set of delta y's of admissible variations are a subspace, and I'm going to show you this in this example right below here. So here is an example. A. This is an admissible set. It's C2 functions on 0, 1. So these are twice differentiable, continuously differentiable functions on the interval 0, 1. And this is a subset of C2 with the value of y at one endpoint being fixed to A and the other endpoint being fixed to B. So, but in between 0 and 1, y of x can be anything so long as it's C2. The set of admissible variations is actually this one I've just listed below, where it's all C2 functions that vanish at both the left and right boundaries. Why? Because if I take any delta y in here and I add it to any y in here, that sum will be in the set A. Because if I take a delta y out of A star and I add it to y, in particular, the boundary conditions will be the same, because this one vanishes. So when I sum them, their sum will be A plus 0, which is still A. So that's this verbal description here of a much more common scenario, which is when admissible variations are subspaces of the original vector space. I'm not going to dwell on this, but here's an example, below here. So not all A stars are subspaces. And a very simple example is, which we will have to contend with later, an admissible set that is all of those y's that have unit length in whatever norm we're talking about. Now the question is A star a subspace? So what does that mean? It means if I take some sort of an h in this vector space and I add it to y, so here we're going to go y plus some number times h. Is this thing in the set A anymore? It should be pretty clear the answer is no, but let's see how that pans out. So I start with a y that I know is in set A. So I know that the length of y is 1. So let's figure out what the length of y plus alpha h is. Well, you use the inner product to expand this out. And then you note that, hey, I've got all of this. I want this whole sum to equal 1. But on the left side, I know this is 1. So that'll cancel the 1 on the right side here. And then I can solve for this inner product here. So y inner product h is equal to this quantity. Now, for some alpha, this will be positive, and so some alpha, this right side will be negative. That can't be. That says that the inner product of a fixed y with a fixed h can both be positive and negative. That's a contradiction. Therefore, these sums cannot be in this set anymore because they can't have unit length. Let's move on. Let's talk about the most important thing. This is it right here. The Gatto variation. Okay, so I'm always going to be talking about an eta, which is in the admissible set. So y's are going to be things that start in the admissible set, and etas are going to be things that are in the admissible variation space. So when I add these two things together, they're still in the admissible set. So I've got j evaluated at something in the set A minus j at something that's in the set A. Okay, so this is this function here, f of epsilon. So I fix a y, I fix an eta, and I say, look, I'm going to multiply this by eta, and eta could be 0, 0.1, 0.2, whatever. That makes a function of epsilon. So for a fixed y and eta, this whole thing is a function of epsilon. And what does this thing mean? It means it's the difference between j at a little distance away from y minus the distance, minus the value of y at y, value of j at y. As such, it might be possible, not always, but it's quite often the case that as a function of one variable epsilon, I can get a Taylor series out of this. And the Taylor series is going to look like, well, whatever f prime of 0 is, times epsilon, plus the second derivative times epsilon squared, etc. This is just a Taylor series expansion of the functional difference. People in different books, they write all this in a different notation. They would write, this top statement could be equivalently written in the following way. The change in y between, that means the change in the value of j between this altered y minus j at the y is equal to something here. This symbol means the variation of y in the direction of eta times epsilon. That's not supposed to have a bar on it. Plus 1/2 delta squared. This is the second variation of j. It is exactly what I've written up here. It is equal to f double prime of 0, whatever that is. Now, I look at this and I say, if y is an extrema, and I go a little distance away from y, say delta y, so this is the slight variation, and I compare the values of j, and if this is the Taylor series expansion of that, then this first term has to vanish if it's a minima. Why? Let's say it didn't vanish. Suppose that thing was equal to 7, so I'd have 7 times epsilon. Well, for positive epsilon, I'd get a positive number. For negative epsilon, I'd get a negative number. How is it possible that then that could be a minima at that point? Because on one side of epsilon, it's bigger. On the other side, it's smaller. So the only way you get around that is to make sure that this first variation has got to vanish. So this one statement I read is the really very, very powerful statement. If I'm looking for an extrema, I have to set this f prime equal to 0, and it has to be true for all etas in the admissible variation set. So here is below, I've defined a first variation. You take, this is f of epsilon up above. I want to take the derivative in epsilon and then set it equal to 0. J's are very general, so without me telling you what J is, I can't compute what this looks like. You can't just say J prime, for example. So, but this statement is, it's either it exists or it doesn't, and it'll depend on what J is and what the set A is. I could also talk about the second derivative of this quantity here in epsilon at epsilon equals 0. So there's a first variation and a second variation, etc. And these are the definitions. Going back again, remember, my goal is going to be to try to find out what that is. It's notationally equivalent to this thing, which is notationally equivalent to this thing. And I want to set that equal to 0. That's going to be the goal. Well, let's see if we can compute these first variations. Sample first variations. So here's one case where the admissible set are the continuous functions on the interval -1 to 1. And if you think about it, the admissible variation space is actually the same space. So that's convenient. It is a subspace of the original vector space. And J of y here it's sort of like an evaluation functional, except what it does, it takes the function y, evaluates it at 0, and then raises that to the 4th power. So that's the functional. So here's this abstract expression here. Let's write down what that actually is. For this J definition, well, this first term here is going to be this sum to the 4th. So y of 0 plus epsilon eta at 0, all to the 4th, minus y naught to the 4th. That's this term here. And I look at that, and that's a power series in epsilon, if you think about it, if I expanded it out. But I can certainly take the derivative in epsilon of that. Some terms will cancel. I'll have an alpha to the y naught to the 4th minus a y naught to the 4th, so that term will go away. But it's just basic calculus here now. Compute the epsilon derivative, evaluate that at epsilon equals 0, and you get this. You get 4 y naught cubed eta at 0. That's the very first variation of that functional for any eta. So you tell me what y is, and you tell me the direction eta for the variation, and I will tell you the first variation. It's this. And I can see now that the requirement that that thing vanish means that this term here is going to have to vanish. Okay, a second example. Here's one with a functional that's defined in terms of an integral, which is more common. Again, I'm going to pick a space where a is a star, and I'm going to define the functional to be this integral. And so let's look at this. So again, it's the same thing that I have to form. J evaluated at y plus epsilon minus j of y. And so that'll be an integral with this term here is going to be replaced by y plus epsilon eta squared minus this square root thing again. And that'll be the difference of two integrals, or it will be the integral of the difference of two things. And when you think about it, when you take the derivative will come underneath the integral sign, and what I'll have to do is evaluating this to get the first variation. So the total derivative becomes a partial under the integral sign. And I've got this expression in here, which has got x's and epsilons, but we're going to be doing a derivative in epsilon. So I do that derivative in epsilon, and then I evaluate at epsilon 0, and I get the following expression. So this is what it is. If I define my functional to be this way, to be this function here, then the first variation at any eta is given by this function above. That's just going through the mechanics of computing these first variations. Okay. So we know what a first variation is. There's this topic on Frechet versus Gâteau derivatives, and I'm not going to talk too much about this, but I'll just explain what the issue is. The issue is very analogous to if you have a function of two variables, say, and you have partial derivatives at the origin, and they exist, does that mean the function is differentiable? And that's a delicate question, but the answer is that no, it need not be differentiable. Differentiability for higher dimensions is a little more complicated. And that kind of requires that you define differentiability in some other manner as opposed to taking partial derivatives under integral signs, etc. So there's a theory behind this, and it says that if I take this difference and I have something called the Frechet derivative for that h, then it is asymptotically small with respect to the norm of h. And if you look at this, it looks almost exactly like f of x plus delta x minus f of x minus f prime of x. And that form it's very analogous to how first derivatives are defined. But these things here are complicated. The derivatives are bounded linear operators on these spaces, and it gets messy. If you ever dive into this, the first thing you should know is that if something has a Frechet derivative, it has a Gâteau variation. We're not going to be dealing with Frechet derivatives. We're only going to be dealing with Gâteau variations. They're way easier to work with, and it's easier to derive necessary conditions for extrema using that. So having said all that, I'm going to move on. This is the main theorem of calculus of variations, period, really. It says that if you have any functional on an admissible set that's a subset of a vector space, and suppose that your admissible variation space is also a subspace of V, then Y bar is an extrema only if the first variation vanishes for all admissible variations. So the difference between this and saying something like f prime equals 0, this is a statement about a derivative which depends on a direction eta. And this derivative has to vanish for all variations. So this is this very, very strong statement here, for all variations, not just. So if j were a function of two variables, this would actually be a gradient, and you'd be talking about directional derivatives, and you'd want to say that the directional derivative is 0 in all directions. That would point to it being a minima, say. So this is a requirement for y bar to be an extrema, and that's how we're going to find extrema later. If you want to know if it's a min or a max, you just go back to that power series of capital F. You've got a second derivative. If the second variation is positive, then it's got to be a local min. So this is it. So what we're going to do is in subsequent lectures, we're going to be considering what is the first variation and how can I make it vanish. That will be used to derive Euler-Lagrange equations. Then sometimes, but not that often, we'll be using this second variation to determine whether or not the extrema found from the first part is a local min or a local max. And then lastly, neither of those, like the second derivative test in multivariate calculus, this will not determine whether it's global max or global min. And I'll have a discussion on how convexity of a functional can be used to find that. So let's just move on. Here's what convexity is all about, really. This picture is, you can't really draw it for an arbitrary functional, but this is the picture you should have in your mind. if I have an admissible set which is convex, so that basically means if you take any 2 points in the set and you do a straight line segment in that set, that entire line segment will be in there. If it's not convex, you could pick points and the line would go outside of your region A. But let's not worry about that too much. So I have a nice convex A. The question is now whether the functional is convex. So the functional to be convex on A, and A has to be convex here too. So for the functional to be convex, this is the statement that defines it. And it's a little hard to understand what this is the first time you see it. The left side here, it says J evaluated on a line segment. And the line segment is parameterized by lambda, lambda going from 0 to 1. At lambda equals 0, this is equal to z. At lambda is equal to 1, this is equal to y. So this thing is the line segment that resides in A. And I'm evaluating J on it. What I've got here is, this is a little different. This is saying, well, what's the straight line from J of y to J of z? And this is saying this quantity, that straight line, is somehow above this thing. So the picture you have in mind is the following. This green curve is the functional evaluated on the straight line segment. And it could change, it could wiggle, it could do all sorts of things. But here I've drawn a case where it's actually convex, like this. And what makes it convex is that when I draw a line segment from any y to any z in the set, I drew this line segment, that this is always below that line. That's what this is saying. A very, very simple functional that is convex are every norm. If you have a norm, it is a convex functional. And the proof is really, really simple. Basically, you just say, well, what's J? If J of y is the norm, then J on the line segment is going to be the norm of the line segment. And then I use the triangle inequality to make that in terms of lambda times the norm of the first y plus 1 minus lambda times the norm of z. And if I look at that and stare at it, that's just J of y and J of z, and that matches this definition up here. So that's a real quick proof that norms are convex functionals. There's a theorem that says that if you have this setup like we're repeating over and over now, J is a mapping from an admissible set that's a subset of some normed vector space. And if it's A is closed, non-empty, and convex, then any local min of the problem is also a global min. You have to remember that when we're talking about this, A could be a bounded set. It doesn't have to go on forever. But this theorem, I will very briefly tell you how this proof works for it. And it's a proof by contradiction. What you do is you assume that y bar is a local minima, but I'm going to try to prove that it isn't a local minima. So let's say it's a local minima, and let's start with that. Well, we know that this line segment's in A, and if J is convex, then we have this inequality here. And then what I do is I just simply rearrange terms. I put things that multiply by lambdas and things that don't multiply by lambdas. So I got a J of y minus some lambda between 0 and 1 times this quantity. Well, if y bar is a minima, then this thing's this whole term here has got to be positive, and this sum has got to be less than j of y bar. But if that's the case, then that contradicts the assumption that y is a local minima, because you're saying that everywhere else on any neighborhood of that point, there are points on this line segment that have a value that are less than that. So those values are smaller than, quote, the local min? I don't think so. So that's a contradiction. So this is a tool. We won't use it too much, but I want you to be aware of it. This is probably the most useful pragmatically from a analytical point of view. It's the easiest to use to show convexity, and it's basically just saying that if these differences are bigger than the derivative or the Gatto variation, then I have a theorem that says that if a function is convex, it's weakly convex, and this property here can be used to show that then it's going to be a global min. Let's show this property first. So let's say, okay, let's suppose I have something that's weakly convex. That means it's a J such that this thing is true. Okay, if that's the case, let's start with something being convex and see if that's true. So here's an example of a J which is convex. This has got to be true. All I'm going to do is I'm going to replace z by y plus eta in here. In there I won't leave y alone, but here I'll have y plus eta. And then I'm going to take that expression and rearrange it, and it becomes the following. So where does this expression, for example, come from? It comes from that term there, being where z is y plus eta. And then I'm going to divide by epsilon. That's where the epsilon on the bottom comes from. So I get this expression being true. Well, this expression is in the limit as epsilon goes to 0 is precisely what you mean by the first variation. So this quantity has got to be bigger than the first variation if j is convex. So if it's convex, it's weakly convex, and you get that expression. Well, if something is weakly convex, there's this last theorem that basically says that it's a unique minimizer, which basically says global minimizer. And the proof is really short and simple. I'll leave you to just stare at that for a second. And this is the one that people generally use. They try to figure out if something is weakly convex to show that there's a global min or a global max. With that, I end, and we'll move on to new things.